Welcome to another video. Today's video is all about launch windows, and we have 4 objectives. Our first is to define what a launch window is. The second is to understand the difference between solar and sidereal time. Third, you should be able to describe and calculate launch window opportunities based on classical orbital elements and the launch site information which we give you. And lastly, you should be able to understand the concept of wait time as it relates to our launch opportunities. So to begin with, what is a launch opportunity? Well, it turns out that our orbit, as it goes around the Earth, is going to be fixed in inertial space. So it's going to be fixed with regards to where the Earth is at. But our launch site is going to be moving. So our launch site is going to be fixed to the surface of the Earth, shown here as a star, and it's going to be, since the Earth is rotating on its axis, moving underneath. And so what you're going to find is if we want to launch directly into this orbit, we're going to have to wait until our launch site moves underneath where our orbit is at, and then we can launch directly into our actual orbit. So we call this a launch opportunity. And so how many launch opportunities we have per day is going to be related to 2 specific quantities. The first quantity is our launch site latitude. So you can see that here is this dotted red line that goes across. So if our launch site latitude was, for instance, here at the Kennedy Space Center out in Florida, we're going to actually have a launch site latitude of 28.5 degrees north. Our projected orbit will have an inclination that you can see here shown as a solid red line. And so that orbital inclination is going to be other quantities. So the first quantity is our launch site latitude, and the second quantity is going to be the orbital inclination. And if our launch site latitude is less than our orbital inclination, we're going to have exactly 2 opportunities that we can launch per day. And why is that? Well, if you can see here from a top-down projection of what we were just looking at, so this would be the North Pole, this is going to be the I vector here. As I start the Earth spinning, our launch site is going to move underneath our orbit twice per day. So you can see the first opportunity was at this first X, the second opportunity is going to be at the second X, and that's going to happen twice per day. We call this first X up here the ascending node opportunity. And why is it the ascending node opportunity? It's because our satellite is going in this direction. So it's ascending from south to north in this way. So since this X is closest to the ascending node, we call this the ascending node opportunity. And this is our descending node opportunity over here for similar reasons. Now, what happens if our launch site latitude is not greater than our orbital inclination? What happens if they're the same? Well, in that case, you're going to have exactly 1 launch opportunity. And so that would look like here with a top-down projection as an opportunity right here at this X. So at this X, that's when our launch site actually spins underneath our orbit. You can think of it that way, where we can launch directly at this moment and we can get directly into this orbit. So our last case is when we have a launch site latitude that's greater than our orbital inclination. And if that's the case, we actually won't be able to launch directly into that orbit at all. So our launch site will just continually be above our orbit. And so what we would have to do in this case is actually launch into a particular orbit and then do a plane change once we're out in space in order to achieve that particular orbital inclination. So that's how we know how many opportunities we have per day, but how do we know when we actually launch? And for that, we're going to have to introduce this other concept called a sidereal time. And we're going to have a sidereal time that's going to relate to our launch site, which is going to be called our local sidereal time. And we're going to have a sidereal time that's going to relate to our orbit, which is going to be our launch window sidereal time, or LWST. And that's what I'm going to talk about here in just 1 minute. So let's start and think about what a solar day is, because this is kind of easy to understand. So a solar day is basically a full day wherein the sun moves from essentially noon to noon overhead. And so if the Earth was not rotating around the sun, if it was just simply spinning on its axis, this would be 360 degrees. But the Earth is rotating on its axis and going around the sun. So in order to get that full noon to noon kind of situation where we get a mean solar day, we have to go 361 degrees approximately on our axis in order to get to the same point per day. Well, that's pretty useful for us as we start talking about, keeping track of time in terms of growing crops and whatnot. But for satellites in orbit, it's less useful to think about our sun's position, and it's more useful to think about just simply the Earth's rotation. And so that's when we're going to introduce this concept of a sidereal day. So a sidereal day is the amount of time it takes the Earth to spin 360 degrees, regardless of where the sun is at. So here you can see it's going to be measured from the I vector, where the I vector points to the first point of Aries, and it's going to be 360 degrees. A solar day is going to be slightly longer than a sidereal day. So a sidereal day is slightly shorter. And here we have what you can do is you can actually measure a sidereal time in terms of where the Earth is in regards to its rotation from the first point of Aries. So here's our launch site latitude shown again, or rather our launch site shown as a star. And it can be moving, and since it's fixed to the surface of the Earth. Since the Earth's rotation rate, it spends 360 degrees in 24 hours, you can know that it goes approximately 15 degrees per hour. And so it's 15 degrees per hour. We can use our Earth's rotation rate as a clock. And we can specify our local sidereal time either in terms of hours or in terms of degrees, as you see here. So as an example, what might the current LST or local sidereal time be of this particular launch site? Well, the Earth is going to be moving in a counterclockwise direction. Since our local sidereal time is 45 degrees away from the first point of Aries, this would be 360 minus 45 degrees, which would be 315 degrees. So you could tell me that the local sidereal time at this moment in time would be 350 degrees or 2100 hours. And of course, that would be changing as the Earth is rotating, but for this snapshot, that's what it would be. Great, so what is our launch window sidereal time? And I mentioned before, this is going to be related to our orbit. So launch window, think orbit. All right, so for a launch window sidereal time, we're going to need to be able to calculate that, and for that we're going to need some angles. So we're going to have some spherical trig that we're going to use, but for the most part, we're not going to ask you to derive those expressions, but we are going to ask you to manipulate those. So here's what our orbital projection would look like on the surface of the Earth. Again, this would be our launch site right here at this star. So at the ascending node opportunity, we're going to introduce some variables here. So our first angle is going to be this angle here between the equator and our orbital projection, and that's going to be alpha. Alpha is going to be equal to our orbital inclination, which is something that we would typically give you in our classical orbital elements. The next angle that you would be given would be this launch site latitude. So the launch site latitude is the angle between the equator and wherever our launch site is. So that's LO, that's our launch site latitude. The next would be gamma, and that's going to be the angle between our line that we drew from essentially the equator along our orbital projection here out to where our launch site is down to the equator along this latitude line. So that's going to be gamma. We call that our launch azimuth. So our launch azimuth, beta AN, is equal to gamma. So how do we know what beta AN is or gamma is? Well, you have to take into account what your orbital inclination is and your launch site latitude. You have both of those things, you take the inverse sine of that, and you have gamma. Next, we have our delta, and delta is this angle here along the equator, which goes from our longitude line to the intersection of this orbital projection and the equator. And we can calculate delta using this expression here, so this is the spherical trig. We put all these together and we get our launch window sidereal time ascending node, which is equal to our right ascension ascending node, which would be from our classical orbital elements, plus our delta. And that's going to tell us when our launch window actually happens in terms of sidereal time. So this is going to be fixed because sidereal time is going to be fixed like that. Excellent. So with that, we can actually figure out how long it takes me to launch into a particular orbit. So for this case, let's look again at a picture here. We've got the North Pole. Here's the projection of our satellite. Our orbit is shown here in green. Our satellite's going to be moving in this direction. I'll show you an animation of that now. Woo! There goes our satellite. Here's the I vector out this way. We have to tell you some more information, like, for instance, let's launch from Vandenberg. So it has a particular launch local sidereal time rather. So LST, its LST is going to be related to this I vector. So at this moment in time, this is what the LST is. How do you figure that out? You go back to the slides before and you essentially use the Earth like a clock. This to me looks like approximately 135 degrees. So here's what our local sidereal time is. Well, the next is we would have to calculate what our launch window ascending node time is, sidereal time ascending node is, and our LWST descending node is. Well, since the satellite is going in this direction, our ascending node opportunity is going to be down here. So that's our launch window sidereal time ascending node. And our descending node opportunity is going to be up here. So here's our descending node. So how long does it take me as someone fixed on the surface of the Earth to rotate underneath this point? Well, it depends on the angular distance between our LST and our LWST-AN. So the wait time for an AN opportunity, either in degrees or hours, either answer would be fine, is the amount of distance, angular distance, or time that it takes me to move from here to here, given that the Earth is going to be spinning at a constant rate. And our descending node opportunity could be calculated thus. And so that's kind of, in a nutshell, how we would go about solving those problems. We're going to do a lot more problems in class, so don't worry if we didn't get too many of the nitty-gritty details on that. We're going to do some more work together in class. But by this point, you should be able to define and to tell me what a launch window is. You should be able to understand what the difference between solar and sidereal time is. We should be able to describe and calculate some basic things about launch window opportunities based on the COEs or launch sites that I give you, and be able to understand the concept of wait time regarding our launch opportunities. Hopefully that helps clarify some issues for you, and we'll see you in class.
Ladies and gentlemen, please, would you bring your attention to me for a feast for your eyes to see, a cacophony of catastrophe. Like nothing you've seen before. Watch closely as I open this door. Your jaws will be on the floor. After this, you'll be begging for more. AKA, let's do another video that is just as fun as the circus. So, here we go. You know who it is. It's me. It's Major Cunningham. Alrighty. Today we're going to be talking about launch windows. Launch windows. So this is one I think of the most misunderstood things in popular culture when people hear about, upcoming launches at Vandenberg or the Cape, and you'll hear stuff like, "Wow, they missed the launch window," or "the launch window closed too soon for them to be able to launch." And so I think there's a little bit of, I think there's a lot, but even if you're not a huge Astro fan, there's a great deal of value in this, so you can kind of debunk people's understanding of, when news about launches comes up and why you might have a weather cancel for a launch and the very specific time window that you have. Anyway, the intent is to kind of walk you through the basics of that. So let's go ahead and do that today. What I'm doing specifically is we have this great exercise that somebody developed to kind of walk you through all the painful particulars, all the exact, specific things about launch windows. A GR might not look quite this nice and organized, and what I mean by that is this wonderful sheet takes you through what all the elements of finding a launch window are, but you might not be given steps 1 through 9. You might just be given question number 8, and you need to do steps 1 through 7. Good thing is, as always, the equation sheet pretty much walks you through it from beginning to end. So, first things first, calculators need to be in degrees mode. Mine is in degrees mode, so that's good. Okay, we'll get rid of that. Okay, all right, so let's take a look at this. So this great exercise here, it gives us some initial orbit information that we'd like to launch into. Remember, we're not actually orbiting yet, but it says we're using one of SpaceX's favorite Falcon 9 rockets. Very famous, right? And we're launching from Cape Canaveral, which is another name for the Kennedy Space Center. And we're allowed to launch basically east-ish, east-north-ish, or east-south-ish, between 35 and 120 degrees. So, and then here's the desired orbital elements that we want to launch into. Alrighty, so first things first, it asks how many launch opportunities exist at this site and why. So, okay, what we do is we look at our inclination that we want to launch into. So that's 50 degrees. And then L sub naught, 0, right? So L sub naught is the latitude of the launch site. And they don't literally label it like that, but they say that the lat long of the launch site, lat long, right, latitude and longitude of the launch site, is 28.5 degrees north at 80 degrees west. So this value is L sub naught. It says that's 28.5 degrees north. Okay, if my inclination I want to launch into is higher up, is bigger than my launch site latitude, I have 2 chances to launch. I can hit the ascending node or the descending node. If my inclination is right exactly at my launch site latitude, equal is what I mean, equal to my launch site latitude, I have 1 chance to launch. It's where the orbit literally just passes right over my launch site. Now, if my inclination of my desired orbit is actually lower than where I'm launching from, I have no chances to launch directly into that orbit. I'll have to do some kind of a burn when I get to orbit, some kind of a simple plane change maybe. Good thing you guys know about some plane changes, but not going to do that in this problem. Not going to do it. Alrighty, so number 2 says, what is the launch? Oh, sorry, for number 1, inclination is bigger than L sub naught. So, sorry, meant to circle that. Yep, so we have 2 chances. All right, number 2, what's the launch or the inclination auxiliary angle? Okay, all these angles that we're about to go through have names that consist of between like 3 and 4 words. It's not so important, my opinion, Cunningham's opinion, that you know or could redraw on a diagram exactly which these angles are or label them with what their long names are. 1 through 5 on here are a kind of just a means to an end. I don't mean to minimize them. They're actually all very important when you're actually launching something, but for our purposes, they're the math that gives us what we really want to know. And what we really want to know is how long from right now, when I hack my watch and say, okay, right now it's a certain time, when can I launch directly into this orbit? Like, how long do I have to wait until I push the big red button that launches this spacecraft? And of course, as we said, depending on our inclination and our launch site latitude, we may have 1 chance, 2 chances, no chances. But if we have a chance, right, between 1 and 2 chances, then we need to know how long we have to wait. And that's what people talk about when they're talking about, we've got a launch window of this much time, and we can only launch directly in that window. And so this is what we're calculating. So, okay, the inclination auxiliary angle is this angle here from the equator to this line coming up to where your launch site is. That's what this little yellow star is supposed to be, is your launch site. So this angle here is alpha. Alpha is actually equivalent to, is the same angle as, the same number as your inclination that you want to launch into. So in this case, this is easy points right here. Inclination auxiliary angle alpha is 50 degrees. Boom, done. Number 3, what is the launch direction auxiliary angle? Okay, so in our little diagram here, and thankfully this diagram is replicated on your equation sheet, but in this diagram, and always, gamma is measured from the longitude line, that comes down from the North Pole and goes right through your launch site around to the line that we drew when we were measuring alpha. So that's what gamma is. Gamma is going to require us to do a little math, but our equation sheet walks us through it, and that's good. It says the sine of gamma is the cosine of alpha, which we just found, over cosine of launch site latitude, which we found from above. So alpha is the inverse sine of the cosine of 50, which we just found, or rather, the angle we just found, over cosine of 28.5 degrees. Let's see here. Make sure your calculator is in degrees mode. Degrees mode, cannot emphasize it enough. Divided by cosine 28.5. Inverse sine of the answer. Good. I get 47 degrees, pretty much right on the money for gamma. Okay. Now, launch window location angle. Okay. So that's the third angle that completes kind of this spherical triangle here, if you will. That is a right angle, but this right here is measured from the point where this line coming up intersects the equator all the way around to where the longitude line that comes down and intersects your launch site then comes down and hits the equator. So again, the little triangle chunk here of the Earth that we're dealing with can be tough to visualize, but the math is really straightforward that the equation sheet walks us through. So let's find the cosine of our launch window location angle, and that is, according to the equation sheet, the cosine of gamma, which we just found, over the sine of alpha, which we just found. So let's plug and chug as we do. Inverse. Oop. Cosine inverse of cosine of 47 degrees, which we just found, over sine of 50. All right, let's see what that gives us. I get 27.103 degrees out of that. Alrighty. Okay, the last kind of housekeeping piece of math that we're going to do is this finding out the launch azimuth, or beta, for the ascending node and the descending node. Now this angle right here is beta, and it's measured kind of, well, let's see, how's the best, this symbol's kind of covering it up. But it is essentially I'll put it this way, whatever you find gamma to be, because of the triangle math, the ascending node opportunity is going to be the same angle. But let's prove that. So launch azimuth of the ascending node, the equation sheet tells us, is literally the same as gamma. Okay, we proved that. Those are equivalent angles. And of course, we found mathematically that that's 47 degrees. That's for the ascending node. Descending node is pretty straightforward too. Of course, we know that's 180 degrees away always from the ascending node opportunity. And the equation sheet helps us with that. That gives us 133 degrees. Okay, so those are our launch azimuths. Now, number 6. Number 6, 7, and 8 start to get to the heart of what we actually want to know out of this whole painful process. What's the launch window sidereal time? Okay, so if I measured from I hat, good old I hat never goes away, right? Always happily pointing out there at the first point of Aries on the vernal equinox, right? That direction, quote unquote, anchored in space, as we know, mostly anchored in space. For our purposes, 100% anchored in space. And then I measured around the equator from kind of a top view of the Earth, essentially, with each, marking off, dividing it up into basically 24 hours a day. Remember back to your ground tracks lesson that the Earth rotates 15 degrees per hour, which makes up for 360 degrees in a day over the course of a 24-hour day. Whew! Okay. Basically, what we're trying to get at here overall is, what is the local time at the point where the orbit intersects the Earth? Let me say that again. So LWST for the ascending node, for example, is basically what's the local time at the location on the Earth where your orbital plane comes up and from the ascending node opportunity intersects the equator. Because we're going to use that, and we're going to subtract what our current local time is at the launch site, and the difference between those two is how long we have to wait. All right, so let's actually march through the math here. So LWST of the ascending node, launch window, sidereal time, LWST, ascending node. Our equation sheet, again, helps us out. It's RAN plus the launch window location angle that we found. And we see that RAN is given to us as 30 degrees up here. That's good. We found our launch window location angle was 27.103 degrees. And that equals, obviously, 57.103. Did it in my head, no big deal. Now, the next step here is we're going to multiply 57.103 times, as I, of course, flip it, the old 1 hour rotation of 15 degrees, so 15 degrees per hour. Again, remember that from ground tracks. And this is going to give you a value. So let's see here. 57.103 divided by 15. So that gives us 3.80. I'm just going to say 807 hours. Well, that seems odd, right? Because, well, if I look down at my watch and it says it is now 0300 in the morning plus 0.807 hours, no one's watch looks like that, right? So the local time is actually 03. We know that part. Plus however much 0.807 of an hour is. So let's see, 0.807 times 60 minutes in 1 hour to make it look human readable. Let's see, we'll multiply that by 60. Okay, and I get that's, so 03 is still true. I'm kind of adding times here, right? So like on your digital watch, the 03 part is the number of hours, and then the minutes, we're going to derive from that 0.807. So I get that is 48 and some change. So I get that it's 0348 local at the launch site, or sorry, at the, oh, not the launch site, at the place on the Earth where the orbital plane happens to intersect the equator, right? Great. So it's 0348 local, early in the morning at that place. Now, that's the ascending node, where the orbit intersects the equator over the ascending node. Great. What about the descending node opportunity? Because we have two opportunities. The problem tells us that. Good thing for us, the equation sheet says LWST descending node opportunity is RAN plus 180 degrees minus that launch window location angle. Okay, so let's again crank through the math. 30 plus 180 minus 27.103. That gives us 182.87. Okay, first things first, 182.87. Let's convert that to a time instead of a degrees. As before, we're going to multiply by 1 hour per 15 degrees. So that gives us 12.191 hours. But now let's convert that to your human readable, time on your watch, your digital clock. So that's 12 hours, right? That's the amount of hours plus 0.191 fractions of an hour, which is to say 60 minutes per 1 hour. We'll multiply that by. And this is going to be I got 12 hours, 11 minutes, plus a few seconds, but we don't go into that detail in Astro. So 1211 local is the descending node opportunity. So put another way, again, the place on the Earth around the equator, right, where the orbital plane at the descending node intersects the equator, that place, so who knows, that'll be somewhere in the tropics or somewhere, in the Pacific or somewhere, it doesn't matter. The place basically on the Earth around the equator where overhead the descending node crosses is 1211, almost little past noon, a little past lunchtime, right? A little past noon local time for them. So you don't have to put the L. That's a force of habit for me. I always put an L to indicate local time, but that's local time for those locations. So maybe I should just get rid of the L to make things less complicated, because that's my goal, trying to make things less, not more complicated. Okay. All right, now number 8. The crux of the matter, finally. If the current LWST at the launch site is 1200, okay, so now we're talking about LST. LST is like the true local time, if you want to call it that, at the actual launch site. So what the problem is saying is that at Kennedy Space Center right now, it's noon. It's like, just assume that you're sitting there in Florida on the coast at Kennedy Space Center and it's noon. So in this case, they tell us it's 1200. You're just about to eat your peanut butter and jelly sandwich. Okay. So the question is then, if that's true, how long do you have to wait for the launch window to open? Tricky. Which opportunity comes first? Well, I tell you what. Let's go ascending node, descending node like we did before. All right. So wait time Now this equation is not on your equation sheet because it's not really, I don't know, I mean, it's not really even an equation. Like if I tell you that you have to go to an event at 7 p.m. and right now it's, 3:30 in the afternoon, or let's use military time. If your event's at 1900 and the current time is 15:30, would you believe that I was like, okay, how much time do you have to get ready? Well, I don't know. You don't have to look at an equation sheet for that. You just know. It's just something from daily life, right? You have 3.5 hours to get ready, or do your homework and then get ready, or whatever. You give yourself these kinds of time estimates on the daily. Everybody does. It's just part of living. Same thing here. So right now, if I say at the launch site, it's 1200, right? It's noon. And then at the launch site ascending node opportunity, as we found, it's 03 in the morning, almost 4, early in the morning. That is how I would write that. Now I'm actually going to implement it a little bit differently than that. Let me put it to you this way. Here is how I typically do this. Looking back at my notes, I measure from the current time to, from the current time at the launch site, basically to the time when, the time at the place on the Earth where the orbit intersects the equator, right? Okay. The equatorial plane, I should say. Here's how I do this. So we found out that launch window sidereal time was 03:48, and our local sidereal time at the launch site is 1200. So what that means is right now it's 1200 at the launch site. And the time at the actual place where the orbit intersects over the equatorial plane, it's 03 in the morning. Okay, just wanted to make sure the facts are clear. I keep repeating them because they are important. So 1200 to midnight, that's 12 hours. That doesn't quite get us to 03 in the morning, so we still have to add from 0000, right, which is the same as 2400 if you want to call it that, to 0348. Let me get rid of that little plus sign. That means that we had to go 12 hours to wait from noon until midnight, plus the additional 3 hours and 48 minutes. So that gives us the wait time for the ascending node opportunity is 15 hours, 48 minutes. Thankfully, the descending node, which I'm going to tell you is the same equation, essentially. The descending node is LWST, descending node minus LST, same as above, right? But thankfully, the descending node opportunity is actually in the near future, right? So 1211 minus our current time at the launch site, which is noon. So the wait time for the descending node opportunity is 11 minutes. Whew, hope we're ready to launch because it's the descending node that's clearly coming up first, right? I have to wait 15 hours, almost 16 hours for my ascending node opportunity. I don't have to wait 11 minutes for my descending node opportunity. Now, okay, last things last. Number 9 says, are there any limitations to which opportunity you choose? And obviously the answer is going to be yes. You could make that argument even if you've never been an astro before. It's like there's always going to be locations and considerations. But what it's getting at is the customer wants to launch in a particular orbit. So did they place any constraints on you as far as where you're allowed to launch? And what I mean by that is, remember our launch azimuths. The customer, well, the government more, I guess, said the allowable launch azimuths are between 35 degrees and 120 degrees. Okay, what we found that our launch azimuth for the ascending node opportunity is 47 degrees. Well, that's good. Because 47 degrees is between 35 and 120. The descending node launch azimuth is 133. Can't use it. Why? Well, because 133 is bigger than the max, right? What's a better way to write this? Because the descending node opportunity is bigger than 120, which is the max, we can't use our descending node opportunity. So there are limitations. Here's how I'd write it. I'd say yes, due to launch site restrictions, we may only use the ascending node launch azimuth. So that means we have to use the ascending node wait time. So despite the wonderful fact that we'd be able to launch, if we were allowed to launch, like physically it's possible for us to launch beyond 130 degrees launch azimuth, but we risk hitting our own people. We don't want to do that. So we just define launch corridors, what they're called, between, for each launch site. So the launch corridor for Kennedy Space Center, or at least as much as the problem tells us, is between 35 and 120 degrees. So we are just going to have to make sure we don't have rocket bodies and toxic stuff falling on people. We're going to go ahead and have to wait for that ascending node opportunity. Oh well. But at least we have a launch opportunity, right? So, okay. So hopefully that helps just walk you through. To give you kind of a quick example, let's see here. Let me show you what it would probably look like closer on a GR or a homework that doesn't have as many intermediate steps helping you. I really recommend trying this problem on your own. I'll leave that on the screen there for a second. But you can see there's only a couple steps. They expect you to do all the steps yourself and just provide the final answers. Thankfully, the equation sheet essentially walks you through the whole thing, with the exception of the wait time. Remember, that's not really an equation. That's an equation at all. It's just, I just got out of class. It's 3:30 right now. I have an event at 7 p.m. in the evening. How much time do I have to get ready? Well, it's that event's time, 7 p.m. minus the current time. So that's how you do that. This was fun chat with you about launch windows. We'll see you next time.